Here we go. So, as I mentioned before, today we are going to talk about reinforcement learning. Reinforcement learning is both very technically interesting and useful, and very philosophically enlightening. There are so many things that you can learn from reinforcement learning that apply to different aspects of making decisions in the real life. What is reinforcement learning? Well, we're dealing with a similar settings to that of MDPs. We have an environment and an agent who interacts with the environment. How does the agent interact with the environment? Well, it performs actions that change the state of the environment, and it receives a corresponding reward. What's the basic idea behind this setting? Well, the agent receives a feedback in the form of rewards. Remember, rewards are scalar values. They're numerical values. And the agent's utility, the thing that a rational being, a rational agent optimizes for, is defined by the reward function. Now, the agent in this environment must learn to act so as to maximize expected rewards. And the learning of the optimal way to act, and by that I mean the optimal way to maximize expected rewards, is based on observed samples of outcomes. Okay, so far this is very similar to the settings of Markov decision processes, right? Well, let me keep you in suspense for a few minutes and show you a few demos of how reinforcement learning is applied in different problems, such as robotics. The very first demo I'm going to show you is the application of reinforcement learning in training a robot dog to walk. Let's look at these demos. This is in the beginning. All right, it got there, but it didn't get there fast enough. It wiggled a little while it was moving forward. Now let's look at how it works during training. And now after training this robot as an RL agent, a reinforcement learning agent. So the difference was a bit subtle here, but if you pay better attention, you'll see that the robot walks with more confidence. It doesn't wiggle, and it goes straight to where it wants to go. Let's look at another example of RL applications in robotics. This is a robotic snake who's learning to move around and climb different levels on objects and so on. That's impressive. Now, let's look at this particular agent. These are all more than 10, 15 years old. The state of RL has changed quite a lot, and towards the end of today's lecture, I'm going to show you more recent examples of RL applications. Now let's see how this bipedal robot works. So it's learning to walk around and remain stable through the use of RL, or reinforcement learning. Now, one more example. This is going to be a running demo for us. It's a toy example or a toy setting. We have this animal. Well, let's call it the square monster, which needs to learn to go from left to right using its claw and the attached arm to the claw. Let's look at the demo.
Okay, so here, what do we see? We see a crawler robot. Its goal, in case you can't tell because it's kind of inept right now, is to move to the right. Whenever it moves to the right, it receives a reward of +1. Whenever it moves to the left, it receives a reward of -1. And its goal is to, over time, maximize its rewards. So it should tend to move right over time. Problem is, it doesn't exactly know what actions make it move right and thereby give it rewards. And it's trickier than you might think. Because in order to move right, you have to spend some time not moving at all as you reset your arm. Now there's some controls here I'll tell you about later. But essentially, it's kind of figuring it out. And if I skip a lot of time, it's going, right? It's off to college. Okay, so you guys will get to build that.
Well, actually, I don't think you'll get to build this particular agent in your project. If I recall correctly, your project is going to be on Ms. Pac-Man, but still we are going to use this as a running demo as well as Pac-Man throughout the lecture. Now, let's dive into the details of the problem. In reinforcement learning, we are still assuming the MDP settings. So we define the problem with a set of states S, a set of permissible actions per state A model, remember the dynamics of the environment, T, which tell us what is the probability of being in state A performing action, being in state S performing action A and ending up in a particular state S prime. So right here, just to refresh your memories, I have to remind you that we're dealing with non-deterministic environments. We are not sure what states we are going to end up in when we are in a particular state and perform a particular action. And there's a reward function R, which tells us what the reward value is when we transition from state A to state S prime by performing action A. And we are still looking for a policy pi, which tells us what action to take when we are in a particular state. All right, so far everything is the same, right? Now here's a difference. In the settings of reinforcement learning, we don't know T or R, so we don't have access to the information represented over these arrows in the plot. In other words, we don't know which states are good or what actions to do. We don't know the probability of ending up in state S prime if we are in the state S and perform action A. And we may not even know the reward that we get if we go through that transition. So how do we solve this problem? Remember, the problem is finding a policy. To solve this problem, we must actually, or the agent must actually try out actions and state to learn. Okay, so let me talk about the main difference between the previous settings of MDPs and the new settings of RL. In MDPs, the agent has already got information about the transition function and the reward function. So when it's in a particular state, it can reason about the future states without actually performing any actions. It can sit down, review its information about the transition function or the dynamics and the reward function, and then make a decision accordingly. However, in RL, since the agent does not have access to those information, it needs to perform actions in the environment to learn what is good and what is bad. So we call the previous settings of MDPs an offline solution. So these are offline because the agent does not have to interact with the environment to make decisions. In the RL settings, the solutions are obtained through online learning. The agent must interact with the environment to be able to find the policy or to be able to learn about good actions and bad actions. Before I go into model-based learning, note that these settings are very similar to Pavlovian conditioning. You've probably heard of conditioning in the context of psychology. I'm going to mention a very, very simple example, and it's this example is that of training a pet, like a dog. So if you want your dog to learn something that you want, not necessarily useful, like rolling over, whenever it rolls over, you give it a treat. Whenever it does something else, you either don't give it a positive incentive, or if you are very strict and not very cognizant of the ethical issues, you may punish the dog. Through this process, your pet, the dog, learns that it's better to roll over when it hears the sound roll over than to do something else. That's essentially the same as RL. Of course, it's a very simplified example. There are arguments that much of the learning that we do as natural instances of intelligence is also based on RL. Specifically, if you're interested, you can look into the dopamine system. Later on today, we'll talk about an algorithm called TD learning, and there are cognitive scientists who believe they can model the process of learning and decision-making in the human brain using TD learning and dopamine transmissions. All right, let's start talking about different approaches to solving the RL problem. The first one we're going to cover is model-based learning. What's the idea behind model-based learning? So in this type of approach, the agent learns an approximate model based on experiences. So the agent does not know what the transition dynamics are or the reward function is. One way to overcome this issue is to approximate those functions, right? And then it solves for values as if the learned model were correct. All right. Let's expand this high-level idea. The first step, as we mentioned, is to learn and approximate or empirical MDP model. Why do we call it empirical? Because it's learned through experimentation. The agent should actually experiment in the environment, perform different actions to be able to learn about the model. In this step, the agent counts the outcomes S prime for each time the agent is in state S and performs action A. So every time the agent is in state S, performs an action A, and ends up in state S prime, the count of this particular transition increments by 1. Then normalize this count to give an estimate of the transition function. Note that we are now denoting the transition function with T hat. That hat means this is an estimate, this is an approximation. And then we discover each reward when we experience that transition. So every time we are in a state S, we perform action A and we end up in a state S prime, we receive a reward signal, right? We can directly record that reward signal as an estimate of the reward that the agent would receive during this transition. Note that here again, the reward function is denoted as R hat, and that hat means this is an approximation. All right, this is step 1. Now that we have T and R, the problem reduces to that of solving an MDP. We have the transition function or an estimate of the transition function, and we also have an estimate of the reward function. So all we have to do in step 2 is to solve the learned MDP. So for example, we can use value iteration just as we did in the previous lecture. Let's look at an example. Imagine the settings of grid world. There is an input policy pi. So we have a fixed policy pi, which is represented in this figure. Remember, a policy tells you what action to take for each state. In state E, the policy tells us to go up. In state C, the policy tells us to go right. In state B, the policy tells us to go right. States D and A are terminal. Now, the agent runs this policy a number of times for a number of episodes from the beginning to the end. In episode 1, the agent begins at state B, it goes east, it ends up at state C, and gets a reward of -1. So every step that the agent takes gets a reward of -1 unless it's a terminal step. Then at state C, the policy dictates that the agent should take action east or right, and it ends up at state D and gets a reward of -1. And then when it gets to state D, it performs the action exit. It ends up at the terminal state. This X represents that the episode has ended now, and gets a reward of +10. Now, the agent repeats this, goes back, restarts the game, if you imagine or consider this as a game, goes back to the beginning. Again, it's at B. It performs the same actions because the policy remains the same, and it gets a similar result in terms of trajectory and rewards. The third time the agent explores, it starts at state E. The policy tells it to go north, so it ends up at C. Then at C, it takes east and ends up in D, and so on. In the fourth episode, again, the agent starts at state E, takes north, ends up at C. Now, here's something interesting happens. Policy dictates that the agent should go east. So the agent performs action east. But since this is a non-deterministic environment, the agent, instead of ending up in D, ends up in A. And then from A, it performs the action exit and gets a reward of -10. All right. Now, what can the agent do with this information? It can come up with estimates of the transition function and the reward function. So what does the transition model, the transition function or the dynamics of this environment look like to the agent? So the transition function is essentially the probability of being in a particular state S, performing action A, and ending up in the state S prime. Based on the experience of this agent, every time the agent is in state B and performs action east, it ends up in state C. So the probability of this happening, this transition happening, seems to be 1 so far, based on the experiences of the agent. What about being in state C and taking the action east? Well, note that in all of these 4 episodes, being in state C and taking action east exists. It actually occurs. In 3 of these episodes, episode 1, 2, and 3, the next state is D, so the agent ends up in D. However, in one of the episodes, episode 4, when the agent is in state C and performs action east, it ends up in state A, right? So the probability based on these experiences, the agent estimates the probability of being in C, taking action east, and ending up in state D as 3/4, which is 75%, and the probability of ending up in state A as 25%. And the rewards are trivially estimated as well. So if the agent is at state B, takes east, and ends up in C, it gets a reward of -1. Why? Because this is what it has observed over all instances, all experiences. Before I move forward, does anybody have any questions? If you do, raise your hand. I can't see the chat box. Whoever is typing, can you please talk to me via audio?
Professor, yes, I have a question.
Okay.
That is not related to this one. Can I do a project on Sudoku?
Sure, you can. We can talk about the projects after the lecture
After
or
that,
during office
sure.
hours.
Yeah,
All
sure.
right.
Yeah, sure. Thank you.
Sure. Any other questions? All right. Let's march on then. Now, just to give you a refresher on calculating probabilities and expected values, let's look at this very simple problem. The goal, our objective in this problem, is to compute the expected age of students in this class. Okay. So remember, expectation is probability multiplied by value, and then the sum of these for each different value. If 3 of you are 25 years old, then 3 out of how many do we have in the class? I think we have 25 students in total in the class. Then the probability of being 25 would be 3 over 25, which is 12%. It would be 0.12 multiplied by 25, plus, let's say we have somebody here who's really young. We have somebody who's 20 years old, but we only have one of those. This probability would be 1 over 25 multiplied by 20, and then we sum all of these together to get the expected age of the students in the class. That's the definition of expectation. Here's a quick example. But what if we don't have this probability for different values? In this case, we instead collect samples, right? I'm going to come and ask each and every one of you, or a random subset of you, how old are you? And then if we want to go with a model-based approach, I'm going to estimate the probability of a student being of a certain age, let's say 20, as the number of samples I've observed whose age is 20 over the total number of samples. This is just a basic definition of sample-based probability, right? Then I can calculate the expected age of everyone in the class using this estimated probability. Note the hat on top of it. This hat refers to, denotes the fact that this is an estimate. This is an approximation. Now there's another approach. First of all, why does this work? Well, because eventually the more samples you get, and if your sampling methodology is accurate, you're picking your samples randomly, you will learn the right model, right? At the limit, I will collect 25 samples, and then I can calculate the accurate probability, right? The assumption here is we have 25 students in the class. Now there's another approach called the model-free approach. In this approach, instead of calculating the probabilities first, we directly calculate the expected age as a direct average of the samples. These two are essentially the same thing, right? Why? Because the probability is the number of times A sub I has occurred over the total number of times. Let's factor out that division. So it would be 1 over n multiplied by the number of times A has occurred multiplied by A, right? Now that's essentially a sum of all values when you do a summation over all of your samples. Why do we call it model-free? Well, it's because we did not explicitly calculate or estimate the probability. We can calculate it. Well, we just skipped a step, and we calculated the expected age of students in the class directly from our samples. What's the advantage of this model-free approach? Well, you have one less computation to perform per sample value. And again, why does this work? Because the more samples you collect, the samples appear with the right frequencies. Any questions about this? Okay. So let's dig a bit deeper into model-free learning. Before that, I'm going to build up to model-free learning through a discussion of passive reinforcement learning. What do I mean by a passive reinforcement learning? Well, let's assume this simplified task of policy evaluation. We've already talked about policy evaluation in our MDP lecture, right? The input to this process is a fixed policy pi, but we don't know the transitions and we don't know the rewards. What's our goal? We want to learn the values of each state. In this case, what we can do is to let the agent just write the policy. The agent, when you have a fixed policy, the agent has no choice about what actions to take, right? The policy is already dictating what actions to take in each state. So the agent just implements the actions that the policy dictates. And it learns from experience. What does that mean? It collects samples and performs approximations. Note that this is not offline planning. This is not the previous settings of MDP that we talked about in the last lecture. Why? Because for an agent to be able to solve this problem, it actually needs to take actions in the world. It actually needs to interact with the world to collect experiences, in other words, samples of transitions and rewards to be able to estimate the transition function and the reward function. So let's talk about the direct evaluation approach for policy evaluation. Again, the goal is to compute values for each state under a fixed policy pi. The idea here is to average together the observed sample values. How do we do this? Well, first we put the agent in the environment and we ask it to act according to pi. In whatever state the agent is, it will do what pi of that state dictates. Remember, pi maps from states to actions. And every time the agent visits a state, it writes down what the sum of discounted rewards turned out to be. And then it averages those samples. This is called direct evaluation. Let's look at an example of this. So we are back to this grid world example. We have an input policy pi as depicted in this figure here, and two terminal states D and A. Now the agent acts or explores the environment, interacts with the environment in 4 different episodes. So the agent gathers 4 sets of transitions and rewards, just as before. These are the same as our previous example. Now, how does it calculate the output values? Let's look at state A, right? How many times do we see state A occurring in these 4 episodes? Only once, down here in episode 4. And what is the expected sum of values from state A, for state A? It's -10, which means that we can just assign a value of -10 to A. Let me see if I can write here. So this is so far -10. And that's a 10. I know my handwriting is not very clear here. What about D? How many times do we observe state D? 3 times in episodes 1, 2, and 3. And every time the agent is in state D, the expected reward, the expected sum of rewards is 10. What's the average of these observations? It's 10 plus 10 plus 10 divided by 3, which is plus 10. Now, what about B? So there are 2 observations from B. In each of these observations, these 2 are identical. So let's solve it for 1. B takes the action east according to the fixed policy, ends up in C and gets a reward of -1. Then from C ends up in D by taking east and gets a reward of -1. And then from D it exits and gets a reward of +10. So what's the sum of rewards? It's 8, right? Now it's the same over here as well in episode 2. So what's the average of the observed sum of rewards? It's 8 plus 8 divided by 2, which is 8. Let's do it for C. Now, in all of the episodes, the agent actually has an observation starting from C. Now, in episode 1, the agent takes east, ends up in D, gets a reward -1, then +10. So the sum of rewards so far is 9. Then, again, this happens here, another 9. What about down here? Another 9. What about over here? It gets -11. So the average reward is 3 times 9. 3 times 9 plus 1 times -11 over 4. What is this value? 27 minus 11 is 16, over 4 is 4. So the value of a state E based on these experiences is approximated to be 4. You can do the same with C. I'm just going to give you the solution now, which gives you +4. All right, any questions? If you have any questions, all you have to do is to raise your hand. There is a button at the bottom of the participants list where, which says raise hand. If you click on it, I'll see that you want to ask a question and I'll call on you. All right, no questions. Let me revert back to nothing. Shantanu?
Could you please explain again for E?
For B?
E for elephant.
E.
Yeah.
Right. So for state E, when you start, you have 4 observations which start from state C. I'm sorry, this 4 here should be up here. I made a mistake. I was calculating the value of C. For state E, I haven't explained. Let me solve it. So all of the explanation I did down here was for state C, which gives us +4. Let me erase this and solve it for E. So how many observations of E do we have? We have 2. In the first one, E goes north, ends up in C, and then the total sum of rewards is 8, right? In the second episode, starting from E, the sum of rewards is -12. So what's the average of these 2 values? 8 plus minus 12 over how many observations are we taking into account? 2, right? Over 2. 8 minus 12 is minus 4. Minus 4 divided by 2 is minus 2. Does that make sense?
Yes, sir. Yes, Professor, I got it.
Very well.
Yeah.
Thanks for the question. I had not noticed that I'd mixed up C with E.
Yeah, I also got confused.
Sorry about that. Thank you.
Yes, sir.
Okay, so let's talk about the pros and cons of direct evaluation. First of all, it's easy to understand. It's really straightforward. And it doesn't require any knowledge of T and R. Remember, in here, we did not explicitly calculate the transition, estimate the transition function or the reward function. We directly estimated the values of the states from observations. So this is an off policy method. I'm sorry, this is a model-free method. It eventually computes the correct average values using just sample transitions. So the more samples you have, the more accurate your estimate becomes. What's bad about it? Well, it wastes information about state connections. It doesn't take into account the connections between these states. And each state must be learned separately. Remember when we wanted to calculate the value of, for example, B, we did not refer to the value of C. We had to do a completely separate calculation for the value of B from what we did to calculate the value of C. You see that there is some overlap between the two, right? If we had the value of C, we could have reduced the computation required to calculate the value of E, the value of B or the value of E. So it takes a long time to learn. Another thing to notice, if B and E both go to C under this policy, how can their values be different? Any thoughts on this? Anyone? So here's the question. B can only go to C. E can also only go to C, right? Why did we calculate different values for state E and state B? See, the value of state B is plus 8. The value that we estimated for state E is negative 2. All right. Shantanu?
So the number of appearances of B and E were different. Means the amount of things we learned were different.
That's somewhat correct, yes. Thank you very much.
Yeah.
So the problem here is, in none of these limited number of observations, starting from B and taking an action, starting from B and ending up in C, C and action East did not act stochastically, did not end up going to A instead of going to D. Why is that? Well, if our states are actually Markovian, it could be because we don't have enough samples in our experiences to actually observe that going from B to C can also result in C going to A. So we don't have enough samples in our in the agent's memory or in the agent's experiences. If you collect more samples, it will be more likely that going from B to C and then performing action east at state C will actually take the agent to state A instead of state D. Why did I mention the Markovian assumption? Because if this is Markovian, where we go from C should not depend on how we got to C, right? That's the definition of Markovian. All right. So why did we not use policy evaluation? Remember policy evaluation? It's essentially simplified Bellman updates to calculate V for a fixed policy. In each round, we replace V with a one-step look-ahead layer over V. So we start by assigning value 0 in the first step to all of the states, and then we keep updating our estimates of V as we move forward in the iterations. So this approach fully exploits the connections between the states. Remember that problem we talked about in direct evaluation, that the connection between states were not utilized? This approach does not have that problem. This approach actually provides a way to utilize the information available from the connections between the states. Unfortunately, if we want to apply policy evaluation, we need T and R. But by definition in RL, we don't have these values. So a key question arises. How can we do this update to V without knowing T and R? In other words, how do we take a weighted average without knowing the weights? All right. So let's see if we can do it. Let's see if we can do sample-based policy evaluation. We want to improve our estimate of V by computing these averages. Why do we call this an average? Well, remember, this is essentially an expectation with T giving us the probability of this value occurring, right? So this is a weighted average. But we don't have T and R. What's the idea here? Take samples of outcomes S prime by doing the action and average. So when the agent is in state S, it performs the action dictated by the policy, and then it gets to state S prime and receives the corresponding reward R. This is going to constitute sample 1 along with the sum of discounted expected reward from state S prime onward. Then the agent takes another sample, and in this sample, being in state S and performing action prescribed by the policy pi, gets it to state S prime 2. And it takes many samples. Now, what does it do with these samples? Here it is, as simple as this. The update in our estimate of the value of state S following policy pi is going to be just an average of the values obtained through these samples. Just an average. As simple as that. Almost. Here's the problem. We can't rewind time to get sample after sample from state S. When an episode begins, if the agent ends up in state S and performs the action prescribed by policy pi, it ends up in some other state and it keeps going, right? You can't force the agent to go back to state S unless state S is one of the possible next states. This is the problem. We can't keep generating. It's not simple to generate multiple samples of being in state S and performing action pi of S in a single episode. So what would an agent do in these settings? The answer is exploration over multiple episodes, but let's wait and build up to it by talking about a very, very fundamental algorithm in RL called temporal difference learning. So what's the big idea behind temporal difference learning? It's to learn from every experience. So essentially, in TD learning, temporal difference learning, we update our estimate of V of S each time we experience a transition starting from S, performing action A, ending up in some other state, and getting the corresponding reward R. Likely outcomes S prime will contribute to updates more often. So the more you get to state S prime, the more this estimate of V of S is going to be biased towards likely outcomes S prime. So temporal difference learning of values is essentially when the policy is fixed, but we are still doing the evaluation. We are evaluating the policy, which means that we are coming up with values of different states. We are trying to estimate the values of different states. The idea here is to move values toward value of whatever successor occurs. Successor means the next step. It's essentially a running average. Let's make it a bit more clear by looking at the math. A sample observed by an agent for value of state S can look like this. The reward obtained from being in the state S, following policy pi, and getting to a particular state S prime, plus the discounted sum of expected rewards from S prime onwards. So how do we update the value of S when we get this sample? The updated estimate of our value of S following policy pi is going to be 1 minus alpha. Alpha is the learning rate, a value between 0 and 1, times V pi of S plus alpha times the sample. What does this mean? Think about it for a second. Ramu?
Maybe we are adding the transition.
Well, the transition has already been observed, right?
In the second statement. 1 minus alpha.
Not exactly. Not exactly.
Okay.
But good guess. Let's further simplify this. This is just a rearrangement of the algebraic terms. This is essentially the same thing. The new estimate, our new estimate of V of S following policy pi is our previous estimate plus the difference between what we've observed and what we expected to see, this is our previous estimate. This is what we expect to see, right? This is our prediction. This is our current estimate. But this is the real observation. So this is telling us how far the sample, the observation is from our estimation. This is essentially an error. And this alpha factor, this learning rate, remember, it's between 0 and 1, is determining how much emphasis we wish to put on this error. So how drastically do we want to change our estimate based on this single observation? The higher the value of alpha is, the more drastic, the larger this change will be. The smaller it is, the smaller this update or this change will be. Let's talk about exponential moving average. Actually, yes, I'm going to ask you if you have any questions after I explain about exponential moving averages. Look at the classical settings of running an interpolation update. So our estimate a new estimate of x at step n is 1 minus alpha. Alpha is, again, the learning rate of value between 0 and 1, multiplied by our previous estimate, or let's say the current estimate of x, plus alpha multiplied by the observation, the actual observation. Note that there is nothing above x of n. It makes recent samples more important. So note that, I'm sorry, these are averages. These are, of course, weighted averages. Note that the most recent sample, and this is an observation, that's why I'm calling it a sample, x sub n is not modulated by a factor of smaller than 1. And then the previous sample, x sub n minus 1, is modulated only by 1 minus alpha. But as it moves forward, the effective learning rate essentially reduces the impact of older samples. It means that the most recent samples are more impactful, have a larger effect on the update than the previous samples. In other words, this interpolation update forgets about the past, which means that distant past values, well, distant past values were not the best. If they were, we would have had a better estimate, right? Now, if the value of alpha decreases as we collect more samples, you can show that this interpolation can converge over time. It doesn't go to infinity. All right. Any questions before I go through an example? You should be full of questions. Anything? All right. I'm going to carry on. I'm going to go over an example of applying this approach numerically. If there is anything that you're doubtful about, and how do you check? You try to explain the concept to yourself as if you're teaching it to someone else. If there's anything that you're not sure about, ask me now. These concepts are really important to grasp before we move forward and build on these topics. Now, imagine the same settings of the grid world. We have 4 states A, B, C, D, and E, assume that the discount factor is 1, so we are not applying discounting just to make things simpler, and a learning rate of half, 1/2. Now, in the beginning, the agent assigns a value of 0 to everything except the terminal state. And as it moves forward, it observes that going from state B to state C through taking action east gives a value of -2. So what does this imply? Remember this update equation? At each iteration, if you look at the values and you plug in the current values like 0 over here for a value of s and apply the update through this observation multiplied by the learning rate, you will get a new value estimate for each of those states. Let me see if I can walk through one of these. So in the beginning, our estimate of the value of state B, for example, is 0. Our current estimate of V pi of B is 0. Then we move east to C and get a reward of -2. And then from C, we move to D and get another reward of -2. What is this -2 here? That's the instantaneous reward observed by the agent in this transition. So this is going to be -2. What's the agent's estimate of the value of the final state of being in state C? So far it's 0, right? So far it's 0. Let me go back a little. So far it's 0. So this is 0. This is the value of being in state S prime, which is the next state after B, which is C, which is 0. So far we have -2 plus 0. What's alpha? It's 1/2. So far, this bit of the update is -1. What about this bit here? What's the initial estimate in the very first step? What's our initial estimate of the value of B? It's 0, right? So this is B. This is 0. 0 multiplied by whatever is 0. So what's going to be our new estimate of V of B if we follow policy pi? It's going to be 0 plus -1, which is -1. And we keep going from here. All right, any questions? No questions? I'm going to take a quiz from this concept. So if you have any questions, it's better to ask it now. Ramu?
Yeah, Professor. From B to C, the reward is -2. From C to D, the reward is -2. Then from D to exit, what will be the reward? Like, how can we calculate? We don't have the next state estimate value from D to exit.
That's correct. So the assumption here is the agent has already started from state D and has noticed that D gives a reward of 8. This has happened before we get to these transitions. And that 8 is a terminal reward.
Yeah.
So when we get to this particular state, the agent already has an estimate of the value of state D. Now note that in here, this observation from C to D has actually not been made yet. So in here, in this transition and in this update, the agent does not know that C will end up in D. It just knows that it was at B, it ended up at C, and the current estimate of the value of C is 0. Does that make sense?
Yeah.
Great. Thanks for your question. Any other questions? Shantanu?
Sir, if you have solved this equation, if we consider the another iteration of this, so next time the value of gamma of v pi s prime would be -1.
Yes, but note that state B is not going to be visited again until the end of this episode. So that observation will be made in another episode. Why? Well, let's see. In this episode, if we go a bit further, this is the concept I was talking about. We can't go back in time. Now that the agent was in state B and it took action east and it ended up in C, it has to move from C, and from C, the policy dictates to go east. It ends up in D and gets a reward of -2. So now in this step, we can update our estimate of V pi of C, and then we can update our estimate of V pi of D as well, if there is any update to be done. Then in the next episode, when we come back to state B, when the agent starts from state B again, or when it observes a transition from state B to state C, its new estimate of the value of state B, let me get the pen again, the value of the new estimate of the value of state B is going to be 1 minus alpha. This is the current estimate of the value of state B, which is -1. As you mentioned, this value would be -1, and so on. Does that answer your question?
Yes, Professor.
Are you sure?
And I also wanted to ask gamma of v pi of s prime, the last one.
Yes.
So what would be the value for next episode for this?
The value of oh, you mean now that we started a new episode and we observed we observed B to C. Now
Yeah.
let's say we go from C to D and get a similar reward.
Yeah.
Now this value is going to be our current estimate of the value of state C. What is our current estimate of the value of state C? We haven't actually calculated it. Let's do it. It's -2 getting to D, and D has a value of, so it would be, let me erase everything. So the current estimate of C is 0. in the very first episode, the current estimate of C is 0. The value of the next state, which is D, is 8. And the received reward for the transition from C to D is -2. So what's going to be our new estimate? It's going to be 8 plus -2, which is 6, multiplied by half, which is 3, plus 0, which means our next estimate, this is pi, imagine that that's pi, for state C in step 1, imagine we start counting the steps from 0, is 3, right?
Yeah. Okay, Professor, got it.
Great. Thanks for that question.
Yes.
Any other questions?
Yeah, Professor.
Go ahead.
Like, does the estimate value of the C will be same if it is going from C to A?
No. If the agent observes a transition from C to E, then the value of the next state changes. Instead of this 8, we'll have 0.
0. Yeah.
Good question. Any other questions?
No.
All right. So can everyone go back to mute, please? Let's move on. Now, there are a few problems with this approach. Remember, we called this technique TD value learning, temporal difference value learning. TD value learning is a model-free way to do policy evaluation, mimicking the Bellman updates we talked about in our last lecture with running sample averages. However, why do we call it model-free? Because in this approach, we are not explicitly calculating or estimating the transition function or the reward function, right? We are estimating the values directly from observations. We are not calculating we are not estimating the transition function or the reward function. That's why we call it model-free. However, if we want to turn values into a new policy, we are sunk. Okay, remember this, pi of state S is argmax over A of the Q function at state S over actions A, and Q itself is defined by this equation here. But since we don't have T, we won't be able to calculate Q, so we won't be able to calculate pi from values observed from values obtained from TD value learning. So what can we do? Here's an idea. Instead of learning the values, let's learn Q values. Instead of estimating the V function, let's estimate the Q function, which also makes action selection model free too. Let's see how this works. Now we are moving past passive reinforcement learning into active reinforcement learning. In full reinforcement learning, we are looking for optimal policies, just like what the value iteration algorithm solved for us. But we don't know the transitions and we don't know the rewards. You get to choose the actions now. So imagine you are in this particular state. You get to choose an action and see what the outcome is. The goal is to learn the optimal policy or the optimal values. In this case, in these settings, the learner makes choices. Remember, the agent gets to choose what action to take at each state. The policy is no longer fixed. The fundamental trade-off here is exploration versus exploitation. This is really important. We are going to talk about this a bit more after the break. The idea here is for the agent to be able to come up with accurate estimates, it needs to have a good number of observations of transitions. And for that to happen, the agent needs to act randomly. It needs to explore different options. But how much should it explore? And how much should it exploit its previous observations? This is a tough challenge. We'll talk about this a little more. And note that this is also not offline planning, because the agent actually takes actions in the world and finds out what happens, right? Now, let's refresh our memories of Q-value iteration. Remember value iteration, the value iteration problem, the value iteration algorithm we talked about before. The idea was to find successive depth-limited values. We start with an initialization of 0 for all states, which we know is right. Then given v sub k, we calculated the depth k plus 1 values for all states. This should be familiar to you all. We've already seen this. But Q values are more useful. Why are they more useful? Remember, it's really simple to go from Q functions or Q values to policy. So let's compute Q values instead. We start with, this is very similar to value iteration. Instead, we're just updating our estimates of Q. In step 0, we start with assigning 0 to the Q value of being in any state and performing any action. Then, given Q sub k, our estimate of Q at step k, calculate the depth Q plus 1 Q values for all Q states, which is essentially represented as this. How is this different from this? First of all, we don't have the max operator anymore, because we're not looking for the maximum value. You're just looking for the value of taking action A in state S. And the other difference is, instead of looking at V sub k of S prime, we are looking at the max over A prime of getting to state S prime from state S by performing action A and performing an action. Note that this is exactly the same as this. So this max of Q is exactly the same as this V sub k of S prime. Now, how can we do sample-based Q value iteration? We don't have this transition function, right? So we have to resort to sample-based or experience-based solutions. The idea is very similar to what we did with sample-based value iteration. Learn Q values as you go. So the agent receives a sample of this form. The agent was in state S, performed action A, got to state S prime and got reward R. Venkatesh, do you have a question?
Yes, Professor. In the previous slide.
Yes.
So you gave me the value of maximum value of Q, but how to find the next iteration then? If there is any next iteration coming up, means how to calculate the next iteration?
You mean this bit here?
Yep.
So remember, this is our current estimate of the Q sub k.
Okay.
Now we are updating our current estimate. So this is going to be our new estimate.
Okay.
It's going to depend on our current estimate of some other value.
Okay.
Remember, this is very similar to what we did in value iteration. In the very beginning, all of these estimates are initialized to 0. And over time, as the agent observes more transitions, these estimates get updated.
Yes. Okay. Thank you, Professor.
Sure. Just to let you in on a secret, it took me a while to make good sense of this process. So if you are not fully confident about your understanding of how this Q sub k plus 1 relates to Q sub k and where does Q sub k come from, do ask me. That was a good question, Venkatesh. Thanks. Now, how can we do sample-based Q value iteration? Why do we want to do that? Because we don't have this transition function. So the idea is to learn Q, S, and the Q values as the agent makes observations and interacts with the environment. So every time the agent performs an action and goes from a state S to a state S prime and receives a state R, a sample of this form is received by the agent. Now the agent considers its old estimate of the Q value. The new sample estimate, consider the new sample estimate is going to be the observed reward. This R, this capital R is the same as this lowercase r value, plus the expected value of the next state S prime, right? Now, how do we incorporate the new estimate into an iterative process and our estimate of our Q function? We use the running average approach. Again, we say that our new estimate of Q of being in state S and performing action A is 1 minus alpha. Alpha is a learning rate between 0 and 1, multiplied by our current estimate of the Q value of S and A, plus the learning rate multiplied by the sample. So if we go back, you can actually rewrite this as, let's see, which is equivalent to Q S A, our current estimate, plus alpha multiplied by sample. I'm just going to, wow, handwriting with mouse is really difficult. Sample minus alpha minus Q S and A. This is the same as what we did for value iteration and value updates using running averages. So we're saying that our new estimate of Q is going to be our old estimate plus a learning rate, alpha, multiplied by the difference between our observed Q value minus our current estimate of the Q value. This is essentially an error. Okay, so some properties of Q learning. This process is called Q learning. Q learning converges to optimal policy at the limit. So the With increasing number of observations, Q-learning gets closer to converging to optimal policy, even if you're acting suboptimally, even if the actions that you're taking are not optimal, Q-learning still converges to the optimal policy. This is amazing, right? This is an amazing result. This is called off-policy learning. Why do we call it off-policy learning? Because we are not following a particular policy here. Venkatesh, question?
But when it comes to the passive learning, it will be slow, right?
What do you mean?
So convergence? No,
Convergence is
yeah.
not necessary. It depends. It depends on the problem. If the problem space is too large, which is the case in many real world problems, yes, Q-learning is going to be very slow. After the break, I'm going to talk about ways of overcoming this slowness.
Okay, Professor, thank you.
Good point. Now, some caveats. For this convergence to happen, we have to explore enough. We have to come up with a good number of observations from possible transitions. And we have to eventually make the learning rate small enough. The learning rate is this alpha. This needs to decrease over time, but it shouldn't decrease too quickly so that we won't overshoot the optimal solution. So basically, in the limit, it doesn't matter how you select actions. This is the same as what we said above here. Even if you're acting suboptimally, it converges. This is based on the assumption that we have an infinite number of observations. So this is true in the limit of infinity. Does this really work in the real world? We can't get to infinity. Yes, yes, it does. You will see later on and in your project that at some point, after having collected a certain number of samples, after a certain amount of exploration, your result is sufficiently close to the optimal values or the optimal policy. All right, so let's take a 5-minute break and let us resume this discussion at 3:20. If you have any questions, in the meantime, let me know.